We're going to move on to states of matter. There are three states of matter: gases, liquids, and solids. Kinetic theory and a model for gases. The word kinetic refers to motion. The energy an object has because of its motion is called kinetic energy. According to the kinetic theory, all matter consists of tiny particles that are in constant motion. The particles in a gas are usually molecules or atoms. The kinetic theory, as it applies to gases, includes three fundamental assumptions about gases. 1. The particles in a gas are considered to be small, hard, sphere-like, and have insignificant volume. Within a gas, the particles are relatively far apart compared with the distance between particles in a liquid or solid. Between the particles, there is empty space. There are no attractive or repulsive forces existing between the particles. The motion of the particles in a gas is rapid, constant, and random. Gases fill their containers regardless of the shape and volume of the containers. An uncontained gas is spread out into the space without limit. The rapid, constant motion of particles in a gas causes them to collide with each other and the walls of its container. The particles travel in straight line paths until they collide with another particle. The particles change direction only when they rebound from collisions. All collisions between particles in a gas are perfectly elastic. During an elastic collision, kinetic energy is transferred without loss from one particle to another. The total kinetic energy remains constant. How does the kinetic theory explain gas pressure? Gas pressure results from the force exerted by a gas per unit surface area of an object. Moving bodies exert a force when they collide with other bodies. Gas pressure is the result of billions of rapidly moving particles in a gas simultaneously colliding with an object. If no particles are present, no collisions can occur. Consequently, there's no pressure. An empty space with no particles and no pressure is called a vacuum. What is the relationship between the temperature in kelvins and the average kinetic energy of the particles? As the substance is heated, its particles absorb energy, some of which is stored within the particles. This stored portion of the energy, or potential energy, does not raise the temperature of the substance. The remaining absorbed energy does speed up the particles, that is, increases their kinetic energy. This increase in kinetic energy results in an increase in temperature. Liquids. A model for liquids. What factors determine the physical properties of a liquid? Substances that can flow are referred to as fluids. Both liquids and gases can flow. The ability of gases and liquids to flow allows them to conform to the shape of their containers. On the bottom, you see some maroon-shaped water, and you see some bromine vapor. Both of them can be poured, and they will conform to the shape of their containers. Gases and liquids have a key difference between them. According to kinetic theory, there are no attractions between the particles in a gas. The particles in a liquid are attracted to each other. These intermolecular attractions keep the particles in a liquid close together, which is why liquids have a definite volume. The interplay between the disruptive motions of particles in a liquid and the attraction among the particles determines the physical property of the liquids. Liquids are much more dense than gases. Increasing the pressure on a liquid has hardly an effect on its volume. The same is true for solids. Liquids and solids are known as condensed states of matter. Evaporation. What is the relationship between evaporation and kinetic energy? The conversion of a liquid to a gas or vapor is called vaporization. When this conversion occurs at the surface of a liquid that is not boiling, the process is called evaporation. The process of evaporation has a different outcome in an open system, such as a lake or an open container, than in a closed system, such as a sealed container. In an open system, molecules that evaporate can escape from the system. In a closed system, the molecules collect as a vapor above the liquid. Some condense back into the liquid. During evaporation, only those molecules with certain kinetic energy can escape from the surface of the liquid. Even some of the particles that do escape collide with molecules in the air and rebound back into the liquid. A liquid evaporates faster when heated. Heating the liquid increases the average kinetic energy of its particles. The added energy enables more particles to overcome the attractive forces keeping them in the liquid state. As evaporation occurs, the particles with the highest kinetic energy tend to escape first. The particles left in the liquid have a lower average kinetic energy than the particles that have escaped. As evaporation takes place, the liquid's temperature decreases. Evaporation is a cooling process. As evaporation occurs, the particles with the highest kinetic energy tend to escape first. The particles left in the liquid have a lower average kinetic energy than the particles that have escaped. As evaporation takes place, the liquid's temperature decreases. Evaporation is a cooling process. You can observe the effects of evaporative cooling on hot days. When you perspire, water molecules in your perspiration absorb heat from your body and evaporate from the skin surface. The evaporation leaves the remaining perspiration cooler. The perspiration that remains cools you further by absorbing more body heat. Under what condition does boiling occur? When a liquid is heated to a temperature at which the particles throughout the liquid have enough kinetic energy to vaporize, the liquid begins to boil. Bubbles of vapor form throughout the liquid, rise to the surface, and escape into the air. The boiling point is the temperature at which the vapor pressure of the liquid is just above the external pressure on the liquid. Boiling is also a cooling process similar to evaporation. Boiling point and pressure changes. Because a liquid boils when its vapor pressure is equal to the external pressure, liquids don't always boil at the same temperature. Because atmospheric pressure is lower at higher altitudes, boiling points decrease at higher altitudes. At sea level, atmospheric pressure, the surface of water is at 70 degrees Celsius, is greater than the pressure of the vapor. Bubbles of vapor cannot form in the water, and it does not boil. At sea level, at the boiling point, the vapor pressure is equal to the atmospheric pressure. Bubbles of vapor form in the water and it boils. Atop Mount Everest, at higher altitudes, the atmospheric pressure is lower than it is at sea level, thus the water boils at a lower temperature. How are the structure and properties of solids related? The general properties of solids reflect the orderly arrangement of their particles and the fixed locations of their particles. In most solids, the atoms, ions, or molecules are packed tightly together. Solids are dense and not easy to compress. Because the particles in solid tend to vibrate at fixed points, solids do not flow. When you heat a solid, its particles vibrate more rapidly as their kinetic energy increasing. The melting point is the temperature at which a solid turns into a liquid. At this temperature, the disruptive vibrations of the particles are strong enough to overcome the attractions that hold them in fixed positions. The freezing point is the temperature at which a liquid turns into a solid. The melting and freezing points of a substance are at the same temperature. At the temperature, the liquid and solid phases are in equilibrium, meaning they're the same. In general, ionic solids have high melting points because the relatively strong forces hold them together. Sodium chloride, NaCl, an ionic compound, has a rather high melting point of 801 degrees Celsius. Sodium chloride solids form a crystal where the particles are arranged in an orderly repeating three-dimensional pattern called a crystal lattice. Molecular solids have relatively low melting points. Sucrose, C12H22O11, a molecular compound, melts at 186 degrees Celsius, which is much lower than sodium chloride, which is 801. Allotropes, diamond, graphite, and fullerenes are crystalline allotropes of carbon. Allotropes are two or more different molecular forms of the same element in the same physical state. Although allotropes are composed of the atoms of the same element, they have different properties because of their structures being different. On the left is the structure of a diamond. In a diamond, each carbon atom in the interior of the diamond is strongly bonded to four others. The array is rigid and compact. Graphite in the middle. In graphite, the carbon atoms are linked in widely spaced layers of hexagonal arrays. On the right is a buckyball, or a Buckminster fullerene. There are 60 carbon atoms form a hollow sphere. The carbons are arranged in pentagons and hexagons. Non-crystalline solids. Not all solids are crystalline in form. Some solids are what we call amorphous. An amorphous solid lacks an ordered internal structure. Rubber, like the rubber balls on the left side, plastic, like the water bottle, and asphalt, like you see the water being dumped on, are amorphous solids. Their atoms are randomly arranged. On the bottom left, I have the natural rubber structure. In the middle, I have a plastic structure, and on the right, I have asphaltene molecules, which are in asphalt, and their structure. Other examples of amorphous solids are glasses. A glass is a transparent fusion product of inorganic substances that have cooled to a rigid state without crystallizing. Glasses are sometimes called supercooled liquids. The irregular internal structure are intermediate between those of a crystalline solid and those of a free-flowing liquid.